thylakoid space stroma. Thylakoid space stroma. I put a buffer out here, which is one of your questions. 6.8 pH, which is a little bit acidic. So the buffer is always going to leave, we'll say, 3 protons out there. If I take one away, what's the buffer going to do? Put one back. If I put an extra one in, what's the buffer going to do? Take one away. So will the buffer maintain the H plus proton concentration gradient?
Yep.
Does it ask you that in your rubric in the lab?
Yep.
Yes. So first step, let's get some water. Got 2 oxygens, 2 hydrogens on each, 2 hydrogens on each. Now I'm going to add an electron, because it takes 2 electrons to make a bond, right? Water, high energy bond or low energy bond? Water, high energy bond, low energy bond? Low. When I put water on a fire, does it flame up or does it go out?
Go out.
It goes out. So, this enzyme, kick water's ACE, because all enzymes end in ACE. Attached to photosystem 2. What does it do to water?
Kick
water's ACE. First thing we're going to do is rip off these 2 oxygens. Can these bond together? 2 electrons per bond?
Yes.
2 covalent bonds?
Yep.
Then the oxygen's going to come out there. We need that later because we want to breathe. Now, electrons are the currency of our atoms. Kick water's ACE is going to rob them, right? So, yoink, 1 electron, yoink, 2 electrons, yoink, 3 electrons, and yoink, 4 electrons.
Yeah.
Now, how many protons do I have in here? 4. And I have 3 out there, so I have more in here. Now, there is a pigment here. It's a green pigment. Who can tell me what the name of that pigment is? First of all, it starts out with the Greek word for green. Chloro, but it's not a flask, green ball. Chlorophyll. So I have chlorophyll. Does the chlorophyll absorb green light or reflect it?
Reflects it.
So it must not like it, right?
Yeah.
Did our green plants grow well?
No.
No. So, energy from the sun hits this chlorophyll, it takes that energy and gives it to the electron. Charge up, charge up, charge up, charge up. Cool? Now what am I going to do? Run, what's this?
Proton pump.
Proton pump. So that uses all its energy. I run 4 electrons through the proton pump. What's it going to pump in?
Hydrogen. Or
4 protons. There's 1. Buffer already replaced it. Check it out. Boom. 2. Buffer already placed it. 3, 4. How many protons inside? How many outside? 8 here, 3 there. Do I have a proton concentration gradient?
Yes.
Is that a question on your lab?
Yes.
What 2 things contributed to that?
Oh, photosynthesis.
Kick water's ACE and the proton pump. Now these are low energy. So photosystem 1, what's that pigment?
Chlorophyll.
So it's the same thing. Charge it up, charge it up, charge it up, charge it up. Right? Now they're charged up, I got to carry it somewhere, don't I? So here I have, I'm going to park this NADP+. Now again, let's look at NADP. If I have NADP, what's the charge?
Neutral.
Positive. I put 1 electron on it. What's the charge? Neutral. I put another electron on it. What's the charge? Negative. I then take one of these protons from outside, and look, yoink, and the buffer did what? Already put another one in footage. What do I have now? NADPH. So could I run this several times and change this 6 NADP pluses into 6 NADPHs?
Yep.
Okay, so we need those for later. Now, how is this an equilibrium, or are there more here and less there? Protons. More here, so the pH here is lower than out there. How do these get out? They can't get out anywhere. Why can't they get out? Well, this is polar, and what's that inside the membrane?
Non-polar.
Oh, so it comes over here, and as they get out, they turn this thing around, and what comes in this side?
ADP.
ADP, and what comes out the other side?
ATP.
So let's run that. Let's say we ran it 9 times. So now I have all these ready to go. So basically, big picture, this is a light reaction. I stored energy from the sun in bonds, here and here, correct? Did I add electrons to that?
Yes.
Did that reduce their charge from positive to that to negative?
Yep.
Therefore, I reduced these. Remember, oxidation reduction. There the line says GER, going way back. I reduced these, I put high energy electrons. But are we finished there? Here's the question. Is it sunlight all the time? Do trees have leaves in the wintertime always? Do trees die every winter? They do.
No.
If you see a tree that's older than a year, it doesn't. So they need to somehow change this into something they can use. So what they do is they need to make sugar. So we're going to use jelly beans. Now, for instance, maple trees, how do they store their sugar? Sap. Maple syrup. How do carrots store their sugar? Yeah, in the ground, in the carrot. How do potatoes store theirs? As a potato. An onion as an onion. Okay, apple trees and many fruits. They either want to make sure that their baby, their seed, has got something to eat, right? So generally around an apple and other fruits, then you have a layer of sweet stuff, which serves two purposes. Number one, to actually give the seed something like when it starts to grow, but the actual purpose is, do animals eat the seeds? Do animals poo?
Yep.
Do they poo right where they ate, or do they take it somewhere else?
Take it somewhere.
That's how those trees got to move around. It wasn't John the Appleseed. It was deer poo. Okay. All right, so now we got to move over here. I need to get over here to Richie. Actually, can I sit there, Richie? Okay, so what I want to start with is, you know, like ruby? That should be a big P. I'm going to have 3 rupees. Ruby P. P for phosphate. This is 3 of these. 1, 2, 3. Every one of these jelly beans is a carbon. So, count. 3, 4, 5. 1, 2, 3, 4, 5. How many is that so far?
None.
1, 2, 3, 4, 5. How many is that?
15.
15. So here I have 15. But remember I said plants need carbon? It can take the carbon air and make it into something solid. So we want to take these carbon dioxides, put these high energy electrons between the carbons and make a sugar. So the first thing I'm going to do is I'm going to add 3 CO2s. Notice how there's already phosphate there. Phosphate from ATP gives it energy.
That's better.
Now with this energy, with these 3 carbons, I'm going to make 6 molecules of PGA. 1, 2, 3, 4, 5, 6. So here I have 15, right? Here I have 3. How many carbons go in each one? How many times 18 divided by 6? 3. So I'll put 3 in there. 1, 2, 3 in there. 1, 2, 3, 3, 1, 2, they're stuck together. 3. So now I have 6 phosphoglyceraldehydes. See them right here? Okay. Now the whole point was, right, I was supposed to store these electrons in here. Agreed?
Yep.
Okay. Who unloads the electrons? ATP. So I have 6 cups. I'm going to take 6 ATPs. I'm going to put them in here. They drop off that high energy phosphate, and what do they become?
ADP.
6 ADPs. I'm going to put that here. Now, can I unload my NADPHs?
Yep.
So here, if I have 6 NADPHs, I actually have 12 electrons. I'm going to drop off those 12 electrons, and what does it become? NADP+. So I just left all these don't have energy now, right? So now, with that energy, these things are going to transform themselves as energy and electrons. Once those phosphates unload the sugar, the electrons, they're going to pop out. Now from this, I make 6 3GPs. So poof, they have the electron, the high energy electrons in there. These are high energy. If you don't believe me, give a whole bag of jelly beans to a younger brother or sister. You will see that sugar has energy. Out of all of this, we get to keep 1. Now, these 5 molecules, we need to change back into this so we can keep on going. Is it going to take energy to change it from this to that? So I'm going to take 3 ATPs, because I'm going to make 3 molecules, put 3 ADPs in, what comes out?
ADP.
3 ADPs, and now I'm back to 3, 3, 3, 2, 2. I'm back to 15. Isn't that where I started? Right. Now, here's my question. In order to make this run, don't I need ATP and ADP and NADPH? Okay, these are all spent. How can I charge these back up again? So, we're in the stroma. These things now, this is going to go back here. What comes in? ADP. What comes out? I just charge that up. What does this do? ATP. What's it become? ATP. NADPHs? NADP pluses, I'm sorry, NADPHs. And the whole time, I'm making oodles of oxygen and stuff like that. And then these are going to come through the stroma and come back to the Calvin cycle. Is that easy peasy?
Yeah.
Okay. So, now, but the thing is, this is not that complicated. The thing is, you guys have to break it down in your notes. And then most important, what should you do with your notes every night for 5 minutes?
Read them.
Just rewrite them, okay? So now what I'm going to do is I'm going to show you guys something on Calvin cycle. You can look it up on YouTube. I typed in Calvin cycle animation, and it's there. All right? You guys can type in Calvin cycle animation. I will tell you how to take your notes. So what I want you guys to do now is, can somebody kind of put all this stuff together for me? I'm going to want everybody to get like a piece of paper and a writing instrument.